All right, welcome back. So, different from the past two sessions, which have been very technical and focused on integration by substitution, today a nice step into the conceptual, so sort of nice back drawing pictures and imagining geometrical regions. Ultimately, in this instance, we are considering an area between two curves. So rather than considering just the area between, say, a function in the horizontal axis or another function in the horizontal axis, what if we consider the region between two functions? Certainly there's some amount of area here, and perhaps using our knowledge of integration, we could deduce the area of this region, well, leveraging what we already know. And in fact, I can think of two ways that sort of naturally one can sort of process the area of this region. So one way is to sort of look at the region holistically. And so that's what I've got here in Roman numeral 1. So we've got our region of area that we're looking at, this region between these two curves. And what you can notice is this region that we're after, the region R, is just the area beneath function f with the area beneath function g taken away, right? Because if you look at the area beneath function f going all the way to the horizontal axis, you essentially want to remove the area that's under function g from the area that's under function f, and you'll get precisely the area that's in between. And so what would this sort of manifest as algebraically? Well, the area under the top function in this case would be the integral from a to b of f of x dx. And over here, we have the integral from a to b of g of x dx. And well, piecing this together, we know using properties of integration, the difference of integrals is just the integral of the difference. And so I'll write this as integral from a to b of f of x minus g of x dx, piecing this all together. So in principle, if you want to think of this as being broken down into the pair of integrals that we originally saw, so be it. That's perfectly fine. These are two algebraically equivalent expressions. And in concept, maybe even this expression with the split integrals helps us think about what the region R is, because it's not all the area that's under F. No, it's the area under F with the area under G taken away. And that's, well, exactly what we've expressed here. So that's sort of one way to look at this area region R. Another way to look at this area region R, I think, is to go back to sort of like a Riemann sum. So imagine the interval between A and B being chopped up into a bunch of tiny pieces and looking then at a rectangular approximation of the area between our two functions. And well, of course, this rectangle is going to be of some small width. We'll call it delta x. But the height of that, well, since the height up here at the top is the height of function f, and the height down here at the bottom of the rectangle is the height of function g, the height of the rectangle itself is just its top value minus its bottom value, right? Big one minus little one will give you the distance in between, and ultimately that would be f of x minus g of x. So if we piece this together, we would get an approximation via our Riemann sum in the form of, well, let's say we have n rectangles in our approximation. We would have each of those rectangles with an area of f of x minus g of x, that's the height, times the width, delta x. And what you can notice is the two expressions that we computed, one for the approximation and the other for the exact value via integral, are actually basically exactly the same in form, right? Well, maybe we've got a delta x here instead of a dx. We know that delta x becomes a dx whenever we let the width of each rectangle go to 0, when we consider the number of rectangles in our approximation going to infinity. And so, frankly, both of these expressions work perfectly well. I will say, so that we don't fall into the trap of simply following this expression formulaically, and instead note that f here has g being subtracted from it because f is in fact sort of our top function. Let me sort of express it like so. If we take f of x and call this our top function, and take g of x and call this our bottom function, maybe it would be better to say the following: the area of region R is the integral from a to b of the top function minus the bottom function dx. So there's a nice sort of complete articulation of these two ideas, taking into account the fact that that our expression f minus g, which appeared below, was really a function of the fact that f was on top and g was on bottom. And then, well, here we have a nice articulation for the area between two curves, and I'll create another video here to work through an example so we can see some of the technical particularities. But in concept, this is the main idea.